Everything you see is a beautiful flaw in a perfect design. The universe began with an elegant symmetry, a single rule governing all forces and particles, as pristine as a flawless crystal. But if that perfection had held, you would not exist. This video will reveal how the cracks in that cosmic crystal created the world you know, from the stars above to the atoms in your hand. We will journey to the first split second of reality to uncover why unity shattered, how a hidden field gave substance to everything, and why a tiny bias between matter and antimatter spared our universe from oblivion. By the end, you will understand not just how the cosmos works, but why it is here at all. What do you think it means that our entire existence hinges on broken perfection? Symmetry is the silent language of the universe, a hidden blueprint written into the fabric of reality itself. Think of that snowflake, its intricate design looking identical whether you turn it by 60 degrees or 120. This invariance, this sameness under change, is the purest form of symmetry, but the cosmos operates on a far grander scale. The most profound symmetries are not about shapes you can see, but about rules that never waver. The law of gravity works the same in a distant galaxy as it does in your backyard. The speed of light is constant whether you measure it today or a billion years from now. This unwavering consistency, this symmetry of physical law across space and time, is what makes the universe comprehensible and stable. It is the reason science is even possible. This idea was crystallized in one of the most beautiful theorems in all of physics, formulated in the early 20th century by the mathematician Emmy Noether. Her theorem reveals a breathtaking connection. For every continuous symmetry in nature, there is a corresponding quantity that is conserved, that can never be created or destroyed. The symmetry of time translation, the fact that the laws of physics do not change from one moment to the next, gives us the conservation of energy. The symmetry of spatial translation, the idea that physics is the same here as over there, gives us the conservation of momentum. These are not just separate facts, they are two sides of the same cosmic coin. The symmetries are the deep, underlying principles, and the conserved quantities, like energy and momentum, are their direct, measurable gifts to reality. This invisible scaffolding of symmetry holds everything together, from the predictable orbit of a planet to the fleeting dance of particles so small they barely exist. It is the universe's operating system, ensuring a stable, orderly cosmos where cause leads to effect and tomorrow can be predicted from today. But if this symmetry is so perfect, so fundamental, why does our world look so beautifully, chaotically broken? Yet that perfect, stable order was not the universe's first chapter. To find its origin, we must journey back to an instant so brief it defies comprehension, a mere fraction of a second after everything began. In that unimaginable dawn, the cosmos was not a place of distinct things, but a state of pure potential. Temperatures soared to levels a billion times hotter than the core of our sun, and in that searing forge, the rules of reality were simplified to their most elegant form. The four fundamental forces we know today, gravity and electromagnetism, and the two nuclear forces, were not separate at all. They were fused into a single, sublime superforce, one law to rule them all. This is the dream of what physicists call a grand unified theory, a mathematical description of that ultimate symmetry. In this state, every particle was massless and identical, zipping through a universe that was perfectly smooth, perfectly uniform, a featureless sea of radiant energy. There were no protons, no atoms, certainly no planets or people. It was a cosmos of breathtaking simplicity, a blank canvas governed by a single, perfect principle. This was the universe in its state of supreme symmetry, and it is precisely this flawless beginning that makes everything that followed so astonishing. For if that perfect symmetry had persisted, reality would have remained forever frozen in that featureless, luminous haze. Our existence hinges on the fact that this perfect state did not last. The universe's entire history, from the first spark of a star to the thought in your mind, is not a story of building up from nothing. It is a story of breaking down from everything. It is the epic tale of that perfect symmetry shattering, and from its fragments our world being born. The flawless crystal of the early universe could not hold. As the cosmos expanded at a blistering rate, it also began to cool, and with that cooling came the first great fracture in reality's design. This moment is known as cosmic inflation, an epoch so brief it makes a blink seem eternal, yet it irrevocably shaped everything we see. In that searing heat immediately after the beginning, the four fundamental forces were fused as one. But as the temperature plummeted, this perfect unity became unstable. Much like superheated steam cannot remain steam as it cools. It must condense, it must choose a new state. The universe faced a similar phase transition. The first force to peel away, to crystallize out of that primordial soup, was gravity. This separation was not a gentle drifting apart. It was a catastrophic release of pent-up energy stored in a field physicists call the inflaton. Think of it like a cosmic spring, wound impossibly tight by the conditions of the newborn cosmos. When the symmetry broke, that spring uncoiled with unimaginable force, driving space itself to expand faster than the speed of light. In less than a trillionth of a second, a region smaller than a proton was stretched to a size larger than our entire observable universe today. This violent smoothing ironed out any wrinkles, creating the stunning large-scale flatness and uniformity we now observe in the cosmic microwave background. But inflation did something even more profound. It took the faintest whispers of quantum uncertainty, the inherent jitter of existence at the smallest scales, and stretched them across the cosmos. Those microscopic ripples in the fabric of spacetime became the grand gravitational seeds for all future structure. Every galaxy cluster, every swirling nebula, every star and planet owes its ultimate origin to those quantum fluctuations, magnified to cosmic proportions by inflation's explosive growth. This was the universe's first and most consequential choice, a spontaneous breaking of its initial symmetry that traded a featureless, perfect unity for a realm rich with potential. It moved the cosmos from being a silent, uniform sea of energy to a canvas imprinted with the faint, gravitational brushstrokes of things to come. The universe was now imprinted with gravitational seeds, but it remained a realm of pure, weightless energy. To build a world of substance, of rocks and rivers and living things, reality needed to break its symmetry once more. This next great fracture gave the cosmos its very texture, transforming ethereal light into tangible matter through a process centered on a field that now permeates every cubic inch of the universe, the Higgs field. In the first searing moments, this field held a value of 0. In this state, particles like the electron and the quarks that make up protons had no mass at all. They were like photons of light, forever destined to travel at the ultimate speed limit, unable to clump together, to attract, to form anything more complex than a fleeting interaction. The universe was a formless dance of radiant energy, but as expansion drove the temperature down past a critical threshold, something profound happened. The Higgs field, like water supercooled and suddenly crystallizing into ice, underwent a cosmic phase transition. It shifted from a value of 0 to a new, stable state, filling all of space with a constant, non-zero value. This event is known as electroweak symmetry breaking, where the electromagnetic force and the weak nuclear force, which had been unified, became distinct. The instant this field switched on, the character of the cosmos changed forever. Now, as particles moved through space, they interacted with this omnipresent Higgs field. Think of it not as a sticky syrup, but more like a cosmic social gathering. A photon, which does not interact with the field, slips through the crowd unnoticed, remaining massless and moving at light speed. But a particle like an electron or a quark engages with the field. This interaction is what we perceive as mass. The more strongly a particle interacts, the more inertia it has, the harder it is to change its speed or direction. This mechanism is why fundamental particles have the specific masses they do. It is the reason an electron has mass, allowing it to be captured by an atomic nucleus. It is the reason quarks have mass, enabling them to bind into protons and neutrons. Without this broken symmetry, atoms could never have formed. There would be no chemistry, no planets, no stars. The confirmation of this brilliant theoretical framework came in 2012 at the CERN laboratory in Switzerland, with the discovery of the Higgs boson. This particle is not the field itself, but a ripple in the field, a tangible excitation that proved the field's existence. Its detection was like feeling the splash from a stone thrown into an invisible pond, finally proving the pond was there all along. This break gave form to the formless. It provided the resistance, the substance, the very thingness that allowed a universe of energy to condense into a universe of matter, setting the stage for gravity to sculpt those primordial seeds into the galaxies we see today. But the universe's work was not yet done. It had forged a world with substance, but a final, critical flaw in the design was needed to make that world permanent. The cosmos now contained matter, but it also contained its perfect mirror image, antimatter. For every particle born in the fiery aftermath of the beginning, an antiparticle should have been created alongside it, a cosmic twin with opposite charge. When matter meets antimatter, they annihilate in a flash of pure energy, leaving nothing behind. If the Big Bang had been perfectly symmetrical, it should have produced these two in perfectly equal amounts. The entire universe would have been a brief, spectacular flash of mutual destruction, a return to light, leaving behind an eternal, empty silence. The fact that you are here to ponder this means that did not happen. Something tipped the scales. A tiny, fundamental asymmetry in the laws of physics themselves allowed one extra particle of matter to survive for every billion annihilations. This is the mystery of CP violation, where the combined symmetries of charge and parity are broken. It means the universe, at its most fundamental level, treats a particle spinning in one direction slightly differently than its antiparticle spinning in the opposite way. This is not a dramatic difference, but a whisper of bias woven into reality's code. The first evidence came from studying the decay of strange particles called kaons in the 1960s. Researchers observed that a neutral kaon and its antimatter counterpart did not decay in exactly identical ways. It was a minuscule discrepancy, but it was real. Later experiments with particles called B mesons confirmed this violation on a larger scale. These delicate measurements, conducted in massive particle colliders, are like listening for a single wrong note in a cosmic symphony played a billion times. They tell us that the laws of physics themselves contain a preference, a rule that distinguishes ever so slightly between matter and antimatter. That preference, imprinted in the universe's first moments, is the reason anything at all survived the Great Annihilation. All the galaxies, stars, and planets are made from that one part in a billion surplus, the ashes of a near-total cancellation. Our existence is not the product of a balanced equation, but the residue of a broken one. Every atom in your body is a testament to a fundamental imperfection, a cosmic favoritism for matter that made all the difference between a universe of light and a universe of life. So while the universe broke its symmetry to give us matter, another powerful force chose a path of perfect, unyielding unity. Deep within the heart of every atom, a different kind of rule holds absolute sway, a symmetry so powerful it has never been broken in the history of our cosmos. This is the domain of the strong nuclear force, governed by a theory called quantum chromodynamics. Its central idea is a beautiful and strange kind of symmetry based on a property whimsically named color charge. Just as electric charge comes in positive and negative, color charge for quarks comes in three types, labeled red, green, and blue. But this has nothing to do with actual color. It is simply a way to describe a fundamental state. The crucial rule is that any particle we can actually observe, like a proton or a neutron, must be color neutral, a perfect blend of all three colors or a color and its opposite. This demand for perfect color neutrality is the unbreakable law that shapes reality at this scale. The force that enforces this law is carried by particles called gluons, and it behaves unlike any force you experience in daily life. Gravity and electromagnetism grow weaker as objects move apart, but the force between quarks is like an ideal rubber band or a strand of cosmic spaghetti. Pull two quarks a short distance apart, and they barely feel a tug, but try to separate them further, and the energy stored in the gluon field between them increases linearly. It does not stretch indefinitely. Instead, when enough energy is pumped into the system, something remarkable happens. The rubber band snaps, but not by releasing the quarks. The immense energy concentrated in the field is converted directly into mass, creating a brand new quark and a brand new antiquark pair, following Einstein's famous equation. The original quarks remain bound, now partnered with these newly created particles. You are left with two new color-neutral combinations, never having found an isolated, free quark. This phenomenon is known as quark confinement. It means the symmetry of color charge is forever locked in a state of perfect preservation. Quarks are eternal prisoners, but their imprisonment is the very reason for our stability. This unbroken symmetry is the glue that binds protons and neutrons together, overcoming the immense repulsive force between positively charged protons to form atomic nuclei. Without this perfect, unyielding bond, nuclei would fly apart, atoms could not exist, and the complex chemistry of life would be impossible. Here, in the fiery core of every atom, a flawless symmetry holds firm, a silent guardian maintaining the integrity of the very building blocks of our material world. This concept of the universe making a choice is not a metaphor, but a precise physical process called spontaneous symmetry breaking. It is the mechanism by which a perfectly symmetric set of laws can produce an asymmetric, richly varied world. To visualize it, picture a ball balanced perfectly on the very peak of an upside-down Mexican hat. The situation is perfectly symmetric. From that central point, every direction down the sloping rim is identical. There is no preferred path, but this symmetry is also profoundly unstable. The slightest breath of air, the tiniest quantum fluctuation, will cause the ball to roll down into the rim. In doing so, it must choose one specific valley out of the infinite possibilities around the circle. The underlying laws, the shape of the hat itself, remain perfectly symmetric. But the actual state of the system, the ball sitting in one particular spot, has broken that rotational symmetry. The system has spontaneously chosen one outcome from many equally valid ones. This is precisely what happened as the universe cooled. The Higgs field was like that ball at the peak. In the extreme heat of the early cosmos, it held a value of 0, a symmetric but unstable high-energy state. As temperatures dropped past a critical point, it became energetically favorable for the field to settle into a new, stable configuration. It rolled down into the rim, adopting a specific, non-zero value everywhere in space. The laws of physics describing the field and its interactions remained symmetric, but the universe's actual condition, filled with this constant Higgs field, was not. This single choice had cascading consequences. Particles that interact with this now present field acquired mass, as we discussed, but the process did something equally profound to the forces themselves. Before this breaking, the electromagnetic force and the weak nuclear force were unified, described by a symmetric set of massless force-carrying particles. When the Higgs field chose its value, it interacted with 3 of these particles in a way that gave them immense mass. These became the W and Z bosons, the heavy carriers of the weak nuclear force responsible for processes like nuclear fusion in the Sun. The one particle that did not interact with the Higgs field remained massless. This became the photon, the carrier of light and electromagnetism. So from one unified force, spontaneous symmetry breaking created 2 distinct forces with wildly different characters, one with short range and massive carriers, the other with infinite range and a massless carrier. The diversity of our physical laws, the very fact that light behaves so differently from nuclear interactions, stems from this spontaneous choice frozen into the fabric of reality. This idea resonates far beyond particle physics. It reveals a deep truth about how complexity and order can emerge in nature, not from an external blueprint, but from a system itself navigating a landscape of possibilities. When water cools, its molecules, symmetric in the liquid state, spontaneously choose a specific crystalline arrangement to form ice. In biology, a uniform cell must choose a front and a back to begin moving, breaking its internal symmetry to achieve function. The universe, in its first moments, faced a series of these spontaneous choices. At each critical temperature, as it expanded and cooled, it rolled down into a new valley on its cosmic landscape, locking in the conditions that would define the next era. Each broken symmetry carved the path toward greater complexity, from a unified superforce to 4 distinct interactions, from massless energy to substantial matter. Our reality is not the product of a single perfect rule, but the layered history of a cosmos that had to choose again and again which imperfect, beautiful form it would take. And with the stage now set, with matter victorious and forces defined, the universe was ready for its next great act, sculpting those gravitational seeds into the grand structures that fill the darkness. The spontaneous choices the universe made were not perfectly coordinated. As the cosmos cooled and those phase transitions unfolded, they did not happen in a single, synchronized instant across the vast, newly inflated expanse. Different regions, separated by distances greater than light could have traveled, made their choices independently. Think of a vast lake freezing over on a cold night. Ice crystals form at many different points, each growing with its own orientation. When these growing crystals meet, their mismatched patterns create fault lines, cracks, and boundaries in the ice. The early universe underwent a similar cosmic freezing, where regions that had chosen different configurations of the Higgs field or different alignments of other fundamental fields met. The clash could not be smoothed away. These imperfections became trapped in the fabric of spacetime itself, frozen relics known as topological defects. They are the cosmic equivalent of scars, permanent records of the violent symmetry-breaking events that forged our reality. Among the most fascinating of these theorized relics are cosmic strings. Imagine a flaw in reality so thin, perhaps no wider than a proton, yet stretching across the entire universe. It would contain the mass energy of a mountain range compressed into every inch, a filament of pure, primordial energy left over from when the forces first split. These strings would not be made of matter, but of space itself in a different, denser state. Their immense gravity would bend light, creating double images of distant galaxies, and as they vibrated or snapped, they would ripple spacetime with powerful gravitational waves. While we have not yet confirmed their existence, finding a cosmic string would be like discovering the fossilized crack in the cosmic ice, a direct snapshot of the universe a fraction of a second old. Other defects are possible depending on the specific geometry of the symmetry that was broken. Domain walls would be two-dimensional sheets separating vast regions of space with different physical properties, like a curtain dividing a room into two distinct realities. Magnetic monopoles would be isolated north or south magnetic poles, particles that carry a magnetic charge, unlike any magnet we know which always has both poles together. The fact that we do not see a universe filled with these exotic objects, especially monopoles, tells physicists something crucial about how the early universe evolved. Their profound absence suggests that the phase transitions were likely smooth and gradual, not sudden and chaotic, guiding the cosmos away from creating such catastrophic defects in abundance. This lack of evidence is in itself a powerful clue, so these hypothetical structures are not just theoretical curiosities, they are tools for cosmic archaeology. If we could detect a cosmic string, it would offer a direct line of sight back to energies and moments far beyond the reach of any particle collider. It would be a tangible piece of the universe's birth certificate, a fossil of broken symmetry that holds the untold story of how our world chose to be. Yet this cascade of broken symmetries gave us more than just matter and forces. It carved the very direction of time itself. Look at the fundamental laws of physics, the equations describing particles colliding or light waves propagating. They are almost perfectly symmetric in time. If you filmed the intricate dance of two electrons scattering off one another and played the recording backward, it would look just as valid, just as real. At the most microscopic level, the universe does not seem to care about past versus future, but your own experience screams otherwise. You remember yesterday, not tomorrow. A shattered glass does not spontaneously reassemble. An egg, once scrambled, stays scrambled. This is the arrow of time, the most profound asymmetry of all, and it emerges not from the laws of individual particles, but from the collective behavior of the entire cosmos. The key is a concept called entropy, often described as the measure of disorder or randomness in a system. The second law of thermodynamics states a simple, relentless rule. The total entropy of an isolated system always increases over time. It is the reason heat flows from hot to cold, never the reverse. It is the reason your room tends toward messiness unless you expend energy to clean it. This inevitable rise in entropy gives time its unmistakable direction, its arrow. But this raises a monumental question. If entropy always increases, pushing the universe toward greater disorder, then it must have started from a state of astonishingly low entropy, of exquisite order. And that starting point was the Big Bang itself. The newborn universe was not a chaotic explosion in the common sense, but a state of incredibly smooth, uniform density and temperature, a configuration of remarkably high order and low entropy. This was the ultimate low-entropy starting condition, the wound-up spring. All the complexity that followed, from swirling galaxies to beating hearts, is the universe unwinding, exploring every possible way to increase its entropy. So where did that pristine order come from? It is intimately tied to the symmetry breaks we have been exploring. The cosmic inflation that smoothed the universe also set its entropy incredibly low. The spontaneous breaking of electroweak symmetry that gave particles mass created new ways for energy to be distributed, new avenues for entropy to grow. The asymmetry between matter and antimatter left a surplus of particles that could interact, collide, and radiate, further driving the increase. The arrow of time is not written into the microscopic rules. It is painted onto the cosmic canvas by the initial conditions and the broken symmetries that followed. We remember the past because it is a state of lower entropy, a more ordered arrangement of the universe's information. The future, toward which we are inevitably drawn, is a state of higher entropy. This is why you can turn an omelette into scattered eggs, but not the other way around. The scramble increases the entropy of the system, moving it along the one-way street carved at the beginning of everything. Our very consciousness, our perception of a flowing present, is a direct consequence of the universe starting in a special, low entropy state and evolving through broken symmetries toward greater disorder. It means the march of time, the feeling of moments slipping from future to past, is not an illusion. It is the universe remembering its own explosive, symmetric birth and telling the irreversible story of its fragmentation into the rich, complex, and fleeting world we call home. Yet the broken symmetries that gave us our world also left deep questions in their wake. One puzzle in particular gnawed at physicists for decades, known as the hierarchy problem. The mass of the Higgs boson is incredibly delicate, a tiny number that must be balanced against enormous quantum corrections from other particles. In our current model, this balance seems unnaturally fine-tuned, like a pencil standing perfectly on its tip for billions of years. It suggested that perhaps our understanding was incomplete, that a deeper, hidden symmetry was protecting this value. This search for a more perfect underlying order led to one of the most beautiful and ambitious ideas in modern physics, supersymmetry. Often called SUSY, this theory proposes a breathtakingly elegant symmetry that goes beyond anything we have discussed. It suggests a profound partnership between the two great families of particles that make up reality. On one side are the fermions, like electrons and quarks, the fundamental building blocks of all matter. On the other are the bosons, like photons and gluons, the force carriers that govern how matter interacts. In our universe, these families are distinct, but supersymmetry posits that at very high energies, perhaps just after the Big Bang, this distinction vanishes. Every known fermion would have a bosonic superpartner, and every known boson would have a fermionic superpartner. The electron would be paired with a selectron, a photon with a photino, a quark with a squark. This symmetry would be a cosmic restoration, a return to a grander, more unified state. The elegance of this idea is not just mathematical beauty, it would solve the hierarchy problem with grace. The quantum contributions from particles and their superpartners would perfectly cancel each other out, naturally explaining the delicate lightness of the Higgs boson without any fine-tuning. Furthermore, it provides a perfect candidate for the universe's most mysterious substance, dark matter. The lightest superpartner, often thought to be something like the photino, would be stable, electrically neutral, and would only interact weakly with ordinary matter, exactly the properties astronomers infer for the invisible mass holding galaxies together. For decades, this made supersymmetry a leading vision for the next layer of reality. The hunt for these superpartners became a primary mission for the world's most powerful microscope, the Large Hadron Collider. Scientists predicted that the tremendous energies of the proton collisions might be enough to briefly recreate the conditions where supersymmetry was intact, causing these exotic partners to flicker into existence. The detectors, vast electronic cathedrals, have been searching meticulously for any signature, any anomaly in the spray of particles that could signal a selectron or a squark. So far, the silence has been profound. No definitive sign of superpartners has emerged at the energies we have probed. This absence does not kill the idea, but it has forced it to evolve, to retreat to higher energy scales. The continued non-discovery forces a profound philosophical question upon us. Is the universe fundamentally symmetric at a level so deep, so hidden by energy, that we may never directly witness it? Or is asymmetry, the very principle of broken perfection that gave us our world, woven into the deepest fabric of existence? Supersymmetry represents the pinnacle of the human quest for a perfect, harmonious underlying reality. Its story, whether one of eventual triumph or elegant surrender, reminds us that our search for cosmic order is also a search for understanding our own place within a cosmos that seems to cherish both symmetry and its beautiful creative break. But perhaps the most humbling asymmetry of all is not about what fills the cosmos, but about the nature of emptiness itself. According to our best theories, empty space is not empty at all. It is a seething, bubbling quantum foam, a turbulent sea of virtual particles and fields flickering in and out of existence on timescales so short they evade direct detection. This relentless quantum activity endows every cubic centimeter of the void with a staggering amount of energy, known as vacuum energy. And this is where our understanding of the very small collides catastrophically with our understanding of the very large. In Einstein's theory of general relativity, energy, including the energy of empty space, creates gravity. This vacuum energy manifests as a term in his equations called the cosmological constant, a kind of innate pressure of the vacuum itself. We now observe that this constant has a tiny positive value, causing the expansion of our universe to accelerate, a discovery that earned a Nobel Prize. The problem, the profound asymmetry, lies in the numbers. When we use quantum field theory to calculate the expected density of this vacuum energy from all those flickering particles, the result is unimaginably large. It should be about 1 followed by 120 zeros times bigger than the minuscule value we actually measure from cosmic observations. This is not a small error. It is the single worst prediction in the history of science, a discrepancy so vast it is like calculating the mass of an ocean and finding only a single drop of water. This chasm between prediction and reality is the cosmological constant problem. It suggests one of two astonishing possibilities. Either there exists a hidden symmetry or a cancellation mechanism of almost perfect precision, one that zeroes out 120 orders of magnitude of energy, leaving behind only the faintest whisper we detect. Or our fundamental concepts of quantum physics and gravity are incomplete, missing a principle that naturally explains why the energy of nothingness is so close to, but not exactly, zero. This is not just a mathematical puzzle. It is a direct question about the stability of reality. If the vacuum energy were anywhere near its calculated quantum value, the repulsive gravity it produced would have been so intense that it would have ripped apart every atom, every nucleus in the first instance of the Big Bang. Stars, planets, and life would have been impossible. The fact that we exist means this did not happen. The vacuum energy is, for reasons we do not grasp, almost perfectly balanced on a knife's edge. Some physicists speculate this could be the ultimate broken symmetry, a cosmic accident frozen into our particular region of a vast multiverse. Others search for a deeper law, a symmetry of nothingness itself, that dictates this near cancellation. This problem stands as the great unfinished chapter in our story of cosmic symmetry, a silent reminder that the greatest mysteries often lie not in the grand structures we see, but in the profound, unsettling quiet of the space between them. The whisper of bias that saved the cosmos from oblivion needed a physical mechanism to carve it into reality. This process is known as baryogenesis, the moment the universe forged its permanent surplus of matter. For it to happen, nature had to satisfy 3 specific and stringent conditions, first outlined by the physicist Andrei Sakharov. Think of them not as separate rules, but as 3 interlocking tumblers in a cosmic lock. All 3 had to click into place for the door to a material universe to swing open. The first condition is a violation of baryon number conservation. In simple terms, a baryon is a heavy particle like a proton or a neutron, the core constituents of atomic nuclei. In the everyday world we see, baryon number is perfectly conserved. You cannot create or destroy the net amount of matter in a chemical reaction or a nuclear decay. You can only rearrange it. But in the extreme energies of the early universe, Sakharov realized this rule had to be breakable. Processes must have existed that could create more baryons than antibaryons from pure energy, tipping the initial balance. The second condition involves the violation of symmetry itself, specifically the combined symmetries of charge and parity. We already saw that CP violation exists, a slight-handedness in the laws of physics that treats particles and their mirror image antiparticles differently. This bias provides the direction, the preference for which side of the scale to tip toward. The third condition is perhaps the most subtle, a departure from thermal equilibrium. In a perfectly hot, uniform, and static soup, every process is reversible. Creation and annihilation are in perfect balance, like a room where for every drop of water that evaporates, another condenses. To imprint a permanent asymmetry, the universe needed a moment out of that balance, a sudden shift where the rules changed faster than the particles could react. The rapid, supercooled expansion of the cosmos during its phase transitions provided exactly this. It was like a snapshot taken while the system was still deciding what to be, freezing a temporary imbalance into a permanent fact. One leading theory for how these conditions were met is called leptogenesis. It proposes that the initial asymmetry did not arise directly among quarks and protons, but first appeared in the ghostly realm of neutrinos. Extremely heavy, hypothetical right-handed neutrinos could have decayed in the early universe, violating the necessary symmetries and producing a slight excess of ordinary neutrinos over antineutrinos. Through subtle interactions, this lepton asymmetry could then have been converted, through a process called Sphaleron transitions, into the baryon asymmetry we see today in all the visible matter around us. It is a cascade of broken symmetry, where an imperfection in one shadowy sector of physics was transferred to become the foundation of everything we see and touch. Baryogenesis is the detailed story of how abstract principles, violations of perfect law, were forged in the heat of the first moments into the concrete bedrock of our existence. Every atom in every star is a direct descendant of that ancient, irreversible event, a fingerprint of the universe's decisive choice to be something rather than nothing. The same subtle bias that saved the universe from emptiness echoes in the very chemistry of your body. Look at your hands, they are mirror images, similar in every way yet impossible to superimpose. This property, called chirality, is not just a quirk of anatomy, it is a fundamental feature of the molecules that make life possible. Amino acids, the building blocks of proteins, and sugars, the backbone of DNA, are chiral. In a laboratory flask, when these molecules are synthesized from non-living ingredients, the result is always a perfect 50-50 mix. You get equal amounts of left-handed and right-handed versions, just as a symmetric universe would demand. But life, in a stunning defiance of that balance, makes a clear choice. Every protein in every organism on Earth is built exclusively from left-handed amino acids. Every strand of DNA and RNA uses only right-handed sugars. This uniform handedness, known as homochirality, is biology's own symmetry break, a puzzle that asks how a perfectly balanced chemical process tipped so decisively to one side. The answer may lie in the stars. When massive stars die or when particles spiral in powerful magnetic fields around neutron stars, they can emit a special kind of light called circularly polarized light. This light twists like a corkscrew as it travels through space, and it can interact differently with the mirror image forms of a molecule, selectively breaking down one-handedness more than the other. Imagine a vast stellar nursery, seeding nascent planetary systems with this subtly biased light, gently enriching cosmic dust clouds with a slight excess of one chiral form over the other. This minute imbalance delivered from the hearts of dying stars could have been the first nudge, but there is another, even more fundamental candidate, a force we have already met in the story of cosmic asymmetry. The weak nuclear force responsible for certain types of radioactive decay is unique. It violates parity symmetry outright, meaning it has an inherent handedness, a preference for interacting with particles spinning in a particular direction. This intrinsic cosmic bias means that left-handed and right-handed molecules would interact ever so slightly differently with the weak force, perhaps during their formation or stability on the ancient Earth. The effect is vanishingly small, but over millions of years in a prebiotic soup, even the faintest whisper of a preference can be amplified. Through processes like crystallization, where a single crystal of one-handedness can template the formation of more like it, or through cycles of dissolution and reformation, a tiny initial asymmetry could have snowballed into the total dominance we see in life today. This is not merely a chemical curiosity. Homochirality may have been the essential gatekeeper for the leap from chemistry to biology. For molecules to begin the complex dance of self-replication, they need to fit together with precision, like pieces of a three-dimensional puzzle. A mix of left and right-handed building blocks creates chaos, molecules that cannot link efficiently to form long, stable chains. By settling on a single-handedness, early biomolecules unlocked a path to complexity, allowing for the intricate folding of proteins and the reliable double helix of DNA. The twist in a strand of sugar, the curl of an amino acid, these are not accidents of evolution. They are the microscopic signatures of a universe inclined toward asymmetry, a cosmic bias that began with the fate of matter itself and cascaded down through the light of stars to guide the first fragile steps toward a living, breathing world. The universe did not cool gently like a cup of tea left on a counter. It underwent a series of violent transformations, each one a cosmic version of water flashing into steam or freezing solid. These are phase transitions, and they are the physical engine behind every symmetry break we have discussed. Just as lowering the temperature forces liquid water to choose a rigid crystalline structure, dropping past certain critical energies forced the universe to choose new, less symmetric states of being. The first of these great changes was likely the separation of gravity, an event tied to the inflationary burst that stretched space itself. Then, as temperatures fell further, came the electroweak transition. Here, the universe was like a superheated liquid, holding the electromagnetic and weak forces in perfect, unified solution. But when the temperature dropped below 100 million billion degrees, that solution could no longer hold. The Higgs field, like water molecules suddenly locking into ice, crystallized into a new value everywhere. This phase change released latent heat and gave mass to particles, but the process may have been spectacularly uneven. Theorists suggest it could have happened through the nucleation of bubbles. Tiny regions of the new, broken symmetry vacuum would have spontaneously formed and expanded at nearly light speed, their walls crashing into each other and filling the cosmos with turbulent energy and potentially gravitational waves. This was not a quiet shift. It was the universe restructuring itself in a storm of released potential. The next great transition sealed the fate of matter itself. As the cosmos cooled to about 2 trillion degrees, the strong nuclear force underwent its own phase change, known as the QCD transition. Before this moment, quarks and gluons existed in a searing, free-flowing plasma called the quark-gluon plasma, a state of matter we can now recreate in particle colliders. It was a symmetric soup where color charge flowed freely, but as the universe expanded and cooled, this plasma underwent a condensation, a cosmic freezing. The unbreakable rule of color confinement took hold. Quarks and gluons were suddenly bound, permanently locked into protons, neutrons, and other composite particles. This was the moment atomic nuclei were forged in the fire of creation itself. Each of these transitions marked a step down a ladder of complexity. With every drop in temperature, the universe lost a degree of symmetry, but it gained a new layer of structure. The perfect, featureless unity of the initial state gave way to distinct forces, particles with mass, and finally, tangible building blocks. This perspective frames cosmic history not as a simple explosion, but as a grand act of condensation. The universe began as a formless, symmetric vapor of pure energy. As it cooled, it precipitated into distinct forces. It condensed further into particles with substance. Finally, it coalesced into the nuclei that would later capture electrons to form atoms. We are the product of this cosmic refrigeration, the complex structures that formed as the heat of creation dissipated into the vast cold of space. The echoes of those violent phase transitions may still be ringing through the cosmos today, in the form of a faint background hum of gravitational waves, a potential whisper from the moment the universe first froze into the shape we recognize. Our universe's visible tapestry of stars and galaxies is held together by invisible threads. The matter we see, the planets and nebulae and everything made of atoms, accounts for less than 15% of the total matter that must exist. The rest is dark matter, a ghostly substance that does not emit, absorb, or reflect light. We cannot see it, but we feel its gravitational hand in everything. Without this hidden mass, galaxies would spin themselves apart, and the cosmic web of clusters and filaments would never have formed. Its existence is one of the most profound confirmations that our standard model of particles is incomplete, a beautiful but partial portrait of reality. This leads to a compelling thought. Could dark matter be evidence of a hidden symmetry, a whole sector of physics operating by its own perfect rules just beyond our perception? The most sought-after candidate for this mysterious substance is known as a WIMP, a weakly interacting massive particle. What makes this idea so elegant is how naturally it emerges from the quest for symmetry itself, particularly from theories like supersymmetry. In that grand framework, every known particle has a heavier superpartner. A crucial feature of many supersymmetric models is a conserved quantum number called R parity. This rule dictates that ordinary particles have even R parity, while their superpartners have odd R parity. In any interaction, the total R parity must be conserved. This has a stunning consequence. The lightest superpartner, perhaps the partner to the photon or the Higgs boson, would have no lighter particle with odd R parity to decay into. It would be absolutely stable, unable to vanish or transform into ordinary matter. Created in the furnace of the Big Bang, these particles would have survived as cosmic relics, drifting through space for billions of years, interacting only through gravity and perhaps the weak nuclear force. They would be massive, they would be weakly interacting, and they would be everywhere. A symmetry we invented to solve one problem, the hierarchy of particle masses, would also solve another, the identity of the universe's missing matter. This elegant connection has driven a decades-long hunt. Deep underground, in abandoned mines and beneath mountains, scientists have built exquisitely sensitive detectors to catch the faintest whisper of a WIMP. These experiments are conducted in profound silence, shielded from cosmic rays by tons of rock, waiting for the rare moment when a dark matter particle might nudge an atomic nucleus and release a tiny flash of light or a minute charge. So far, the silence persists. Other experiments look for indirect evidence, scanning the skies for the telltale gamma rays or other particles that might be produced when two WIMP annihilate each other in the dense heart of our galaxy, or in dwarf galaxies rich with dark matter. The null results have tightened the constraints, telling us what dark matter is not, but the core mystery remains. This ongoing search forces us to consider an even grander possibility. Dark matter may not be a single particle, but the tip of an entire hidden cosmos. It could be part of a dark sector with its own particles, its own forces, and its own unbroken symmetries that govern interactions we cannot see. In this view, our luminous universe of atoms and light is just one facet of existence, intertwined gravitationally with a vast shadow realm that operates by a different, perfectly symmetric set of laws. The gravitational effects we witness, the way dark matter bends light in gravitational lenses and sculpts the large-scale structure of the cosmos, are merely the echoes of that other reality pressing into our own. If this is true, then dark matter is not just a missing ingredient. It is a messenger from a parallel universe of physics, a clue that the symmetry breaking which defined our reality left an entire domain of perfection intact, silently holding the stars in their places. The cosmic shadows cast by dark matter are mirrored by the subtle transformations of the universe's most elusive travelers. Neutrinos are cosmic phantoms streaming from the sun, from exploding stars, and from the Big Bang itself, passing through your body by the trillions every second without a trace. For decades, physicists believed these particles were perfectly massless, as the Standard Model demanded, zipping through the cosmos at light speed and existing in three distinct and permanent identities, or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. This was a simple, symmetric arrangement, but the universe, as we have learned, has a preference for complexity. In the late 1990s, a vast experiment buried deep in a Japanese mine called Supersymmetry witnessed something impossible. It was designed to catch neutrinos produced in the atmosphere when cosmic rays strike air molecules. The detector, a giant tank filled with 50,000 tons of ultra-pure water lined with sensitive light sensors, should have seen equal numbers of neutrinos coming from straight above and those that had traveled all the way through the Earth. They did not. A significant fraction of the muon neutrinos that came up through the planet were missing. They had not vanished, they had changed. On their long journey through the Earth, they had morphed or oscillated into a different flavor that the detector could not see as easily. This was the first definitive proof of neutrino oscillations. The implications were staggering. For a neutrino to oscillate, it must experience the flow of time differently than a particle moving at light speed. This meant unequivocally that neutrinos have mass. It was a crack in the flawless facade of the Standard Model, a direct observation that this foundational theory was incomplete. The symmetry between the three neutrino families was broken. Further confirmation came from the Sudbury Neutrino Observatory in Canada, which solved the long-standing solar neutrino problem by showing that electron neutrinos produced in the Sun's core were transforming into other flavors on their way to Earth. But how does this strange metamorphosis work? The key lies in a quantum mismatch. The flavors we label and detect, electron, muon, tau, are not the particle's fundamental mass states. Instead, each flavor neutrino is a quantum mixture, a specific blend of three different mass states. Think of it like having three pure primary colors of light, each with a slightly different property. What we call an electron neutrino is not a single color, but a specific combination of all three, projected onto a screen. As the neutrino travels, these underlying mass states evolve at slightly different rates due to their different masses, like waves falling out of sync. By the time the neutrino reaches a detector, the mixture has changed, the original combination has shifted, and when we project it onto our detection screen again, it might now register as a muon neutrino. The flavor is not a permanent tag. It is a fleeting snapshot of a deeper quantum reality. This constant, invisible dance is a living, breathing example of symmetry breaking in the quantum realm. The perfect, one-to-one correspondence between a neutrino's identity and its state is shattered by the reality of mass. Every oscillation is a quiet testament to the universe's imperfect foundations, written in the language of the most ghostly particles we know. And this very phenomenon, this quantum mixing, may be intimately connected to the grandest asymmetry of all. The same physics that allows neutrinos to oscillate could also have provided, in the universe's first seconds, a mechanism to tip the scales between matter and antimatter, making those oscillations not just a curious detail, but a potential key to our own existence. Gravity is the cosmic force we know best, the anchor of planets and the architect of galaxies. Yet in the subatomic realm it is a ghost. The four fundamental forces operate on scales so different it defies intuition. The strong nuclear force that binds atomic nuclei is about 100 times stronger than electromagnetism, which is itself roughly 1,000 times stronger than the weak nuclear force. And then there is gravity. To feel its staggering weakness, picture a simple refrigerator magnet. the tiny electromagnetic force from that magnet can lift a paperclip off a table, effortlessly overcoming the gravitational pull of the entire planet Earth beneath it. This vast chasm in strength, known as the hierarchy problem, is one of the deepest puzzles in modern physics. In a universe born from perfect symmetry, why would one force be so unimaginably feebler than the others? It feels like a design flaw, an unnatural imbalance that suggests our understanding is missing a crucial piece. If all forces were unified at the beginning, as our theories suggest, they should have emerged from the cooling cosmos with more comparable strength. The fact that gravity did not hints at a profound broken symmetry or a hidden structure we have yet to perceive. This is not just a numerical curiosity, it is a direct challenge to our quest for a unified theory of everything. The problem becomes even sharper when we look at the Higgs boson. The mass of the Higgs is intimately tied to the scale of the weak force, but quantum mechanics suggests that the Higgs mass should be pulled up to an enormous value, near the scale where gravity becomes strong, due to virtual particles constantly popping in and out of existence. To keep the Higgs light enough for our universe to exist, an almost perfect cancellation must occur, a fine-tuning of 1 part in a trillion trillion. To many physicists, such a precise, unnatural balance is aesthetically unsatisfying. It feels like the universe is balancing a pencil on its tip for eternity, and we are left wondering what invisible hand is keeping it steady. This desire for a more natural, elegant explanation drives the search for new physics. One leading idea, supersymmetry, proposes that every known particle has a heavier superpartner. The quantum contributions from these partner particles would perfectly cancel out the problematic corrections to the Higgs mass, solving the fine-tuning issue with mathematical grace. In this elegant framework, the weakness of gravity relative to the other forces could be explained by the specific energies at which these symmetries broke. Another, even more mind-bending proposal involves the very fabric of space itself. What if our universe has more than the 3 spatial dimensions we experience? In some models, the 3 other forces are confined to our familiar 3-dimensional brain, like waves trapped on the surface of a pond. Gravity, however, could be the only force that permeates extra, compactified dimensions curled up at scales too tiny for us to detect. In this picture, gravity appears weak not because it is inherently feeble, but because its influence is diluted, leaking out into these hidden realms. We only feel a faint shadow of its true strength. Each of these ideas represents a different path toward restoring a lost symmetry, a way to make the universe's rulebook feel whole and natural again. The hierarchy problem, then, is more than a technical issue. It is a beacon guiding us toward a deeper layer of reality. It asks us to question whether the asymmetry we measure is the final word, or merely a hint of a grander, more symmetric truth waiting to be discovered in the echoes of the next great experiment. But the story of cosmic symmetry does not end with our present. It stretches forward into an almost unimaginable future, a timeline measured not in billions, but in trillions upon trillions of years. Based on everything we observe, the universe's expansion is not slowing down, it is accelerating, driven by that mysterious dark energy. This points toward a likely final chapter known as the heat death. In this distant epoch, the last stars will have burned out, their ashes scattered. Galaxies will have drifted apart into an ever-expanding darkness. Even the mightiest black holes, after slowly evaporating over eons through a process called Hawking radiation, will fade into whispers of particles. All temperature differences, all energy gradients that power stars and planets and life itself, will have smoothed away. The cosmos will approach a temperature of absolute zero, a state of maximum entropy where nothing happens, because everything is everywhere the same. This is a chilling symmetry of nothingness, a return to a uniform void. But unlike the hot, dense, and potent uniformity of the Big Bang, this cold uniformity is sterile. It holds no potential, no hidden quantum seeds. It is a symmetry of equilibrium, of perfect and final stillness. The broken symmetries that sparked galaxies and gave particles mass would, in this view, be a temporary flourishing in an eternal march toward a silent, featureless end. Yet this stark picture is not the only possibility written in the mathematics of cosmology. Some theories paint a more cyclical vision of eternity. Could the universe be engaged in an endless cosmic heartbeat, a cycle of expansion and contraction? In one such model, known as the Big Bounce, our expanding universe might eventually slow, reverse, and collapse back upon itself in a great crunch. As it compresses, temperatures and densities would soar back to those unimaginable levels, perhaps erasing all structure, melting protons and neutrons back into a quark-gluon plasma, and ultimately restoring the perfect, symmetric state of the earliest moments. Then, from that fiery, singular point, a new Big Bang could erupt, birthing a new universe with its own set of broken symmetries, its own laws, and its own chance for complexity. In this breathtaking scenario, our entire cosmos, with all its beauty and fragility, is but one phase in an eternal rhythm. The broken symmetries that define our reality would not be permanent, but a recurring phase, like ice crystallizing each time a pond freezes, each time with a slightly different pattern. Weighing these two futures is a profound exercise. The heat death is the direct extrapolation of the laws we see in action today, a sobering but logical conclusion. The cyclic model offers a poetic sense of renewal, but requires physics beyond our current confirmation, such as a form of dark energy that changes over time to allow for collapse. Both speak to a deeper question about the nature of cosmic symmetry itself. Is the universe on a one-way journey from order to disorder, from a symmetric beginning to an equally symmetric but lifeless end? Or does it move through phases where symmetry is broken to create a temporary world of complexity, only to be restored and broken again in an infinite dance? Our existence today, in this vibrant middle chapter, depends entirely on the broken symmetries we have explored. Whether they are a single, brilliant accident in a march toward cold silence, or one note in an endless symphony of creation and dissolution, they are the reason we are here to ask the question. The universe's final symmetry, be it one of cold stillness or fiery rebirth, remains its greatest unresolved mystery, written in the fate of the very same forces that gave us light, matter, and time. The final frontier in our quest for cosmic symmetry lies at the very edge of understanding, where our two most successful theories of reality stare at each other across an unbridgeable chasm. On one side stands quantum mechanics, the exquisitely precise rulebook for the subatomic world, a realm of probability, uncertainty, and shimmering potential. On the other stands Einstein's general relativity, the majestic description of gravity as the curvature of spacetime itself, governing planets, stars, and the cosmos on its grandest scales. Each theory is breathtakingly accurate within its own domain, yet they are fundamentally incompatible, speaking different mathematical languages and describing a universe that cannot be both at once. This conflict is the greatest unsolved problem in physics, and its resolution demands a vision of symmetry so profound it would dwarf all that came before. The dream is a theory of quantum gravity, a single, elegant framework that would weave these two disparate pictures into one seamless tapestry, finally placing gravity under the same quantum rules as the other forces. This would be the ultimate restoration, a glimpse of the perfect, unified symmetry that existed at the universe's very birth. To find it, we must venture to a scale so small it defies imagination, the Planck scale, where the fabric of spacetime is believed to dissolve into a seething quantum foam. Here, distances are 100 billion times smaller than an atom, and our conventional notions of space and time simply cease to have meaning. In this primordial realm, physicists believe a supreme symmetry awaits discovery, a single principle from which all forces and all particles emanate. The quest to unveil this principle is not merely technical, it is a philosophical journey to answer the most fundamental question of all: what is the irreducible essence of reality? Leading this quest are several brilliant yet unproven visions of the quantum gravity universe. The most prominent is string theory, a framework of astonishing mathematical beauty. It proposes a radical shift in perspective. The fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops or strands of energy strings. Just as different vibration patterns on a violin string produce distinct musical notes, the different resonant frequencies of these fundamental strings give rise to the entire particle zoo: electrons, quarks, photons, and all the rest. In this symphony of strings, even gravity finds its place, carried by a specific vibrational pattern called the graviton. The elegance deepens with the theory's demand for extra dimensions. For the mathematical harmony to work, strings must vibrate in a spacetime of 10 or 11 dimensions. We experience only 3 of space and 1 of time. The remaining 6 or 7 are thought to be curled up or compactified at the Planck scale, their intricate geometry determining the properties of the forces and particles we observe. String theory, in its ideal form, is a vision of ultimate unity, where all of nature's diversity emerges from the symmetrical vibrations of a single type of object in a higher dimensional space. Yet this beautiful dream confronts immense challenges. The first is the landscape problem. The way those extra dimensions curl up is not uniquely predicted by the theory's equations. Instead, there appears to be a vast landscape of possible configurations, perhaps 10 to the 500 different ways, each corresponding to a universe with different physical constants and laws. Our universe, with its specific particle masses and force strengths, would be just one possibility among a near-infinite array. This leads to a profound philosophical shift. The laws of physics we measure might not be the only logical possibility, but simply the outcome of a cosmic accident, a particular symmetry-breaking path our region of reality took. Another major challenge is testability. The energy scale required to probe these strings or see evidence of extra dimensions is far, far beyond the reach of any particle collider we could ever build. This forces the search onto 2 fronts: the mathematical consistency of the theory itself and the hunt for subtle, indirect signatures in cosmological data, such as specific patterns in the cosmic microwave background or in gravitational waves from the earliest moments. String theory is not the only path toward unification. A compelling alternative is loop quantum gravity. This approach takes general relativity as its starting point and applies the principles of quantum mechanics directly to the fabric of spacetime. Instead of smooth continuity, it proposes that space itself is woven from a network of finite, quantized loops, a spin network. In this picture, area and volume come in discrete, tiny packets, a pixelation of reality at the Planck scale. This provides a natural way to avoid the infinities that plague other attempts to quantize gravity and offers a potential glimpse of what happened at the Big Bang singularity, possibly describing a universe that bounced from a previous cosmic phase. While less focused on unifying all forces into one, loop quantum gravity provides a starkly different, yet deeply compelling vision of quantum spacetime, emphasizing the relational and discrete nature of geometry itself. Whether through the vibrating strings of one theory or the woven loops of another, the pursuit of quantum gravity represents the pinnacle of humanity's search for cosmic symmetry. It is an endeavor that stretches the limits of mathematics and imagination, asking us to conceive of dimensions beyond perception and a reality more fundamental than particles or forces. This is not just science, it is a form of cosmic archaeology, digging through the layered breaks in symmetry that shaped our world to uncover the pristine, unified law that started it all. The ultimate theory, if we ever find it, would complete the circle, revealing how the flawless symmetry of the beginning necessarily fractured to produce the rich, complex, and beautifully imperfect universe we call home. It would tell us not just how things work, but why this particular world, with all its broken rules and glorious structure, had to be. This leads us to a question that is as unsettling as it is profound. Why do the fundamental constants of nature have the precise, life-permitting values they do? The strength of gravity, the mass of the electron, the energy of empty space, each seems delicately balanced on a razor's edge. Tweak anyone by a tiny fraction and stars would not ignite, atoms would not bond, and the universe would be a sterile void. This staggering fine-tuning suggests our cosmos is not just accidentally hospitable, but almost suspiciously engineered for life. This observation gives rise to a powerful and controversial line of reasoning known as the Anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We should not be surprised to find ourselves in a universe with broken symmetries that allow for planets, chemistry, and conscious life, because we could not be anywhere else. It is a cosmic version of the old joke about a puddle marveling at how perfectly the hole in the ground fits its shape. The puddle thinks the hole was designed for it, when in reality, it simply conformed to the hole's pre-existing shape. In this view, our universe's specific asymmetries are not the result of a single, destined path, but rather the only type of path we could possibly witness. This idea moves from philosophical curiosity to a potential scientific framework when paired with the concept of a multiverse. Imagine a vast cosmic landscape, a frothing sea of bubble universes, each born with its own random set of physical constants and symmetry-breaking patterns. In most of these bubbles, the numbers are wrong. Gravity is too strong and all matter collapses instantly. The cosmological constant is too large, ripping space-time apart. The asymmetry between matter and antimatter is zero, leaving nothing but empty radiation. These are dead universes, silent and unobserved. But in a vanishingly small fraction of the bubbles, by pure chance, the numbers fall within the narrow window that allows for galaxies, stars, planets, and eventually, life. We, of course, find ourselves in one of those rare, fruitful bubbles. Our existence is not a clue to a grand design, but a statistical inevitability. We are simply the inhabitants of a universe that won the cosmic lottery. This reframes every mystery we have explored. It shifts the question from why did symmetry break this exact way, to what does our observation tell us about the landscape of all possible breaks. The weakness of gravity, the specific masses of particles, the tiny value of the cosmological constant, these are not fundamental truths of all reality. They are local bylaws, the unique environmental conditions of our particular cosmic neighborhood. This perspective is both humbling and liberating. It suggests that the search for a single, elegant equation describing why our constants must be what they are may be futile. There is no why, only a where. We live in a universe that allows the question to be asked. The Anthropic principle is often criticized for seemingly explaining too much by explaining nothing, for replacing physics with a tautology. Yet its power lies in its predictive restraint. It tells us not to be surprised by fine-tuning, and it guides us to look for other signatures of a multiverse in the patterns of the cosmic microwave background or the behavior of dark energy. It transforms our place in the cosmos. We are not the predetermined pinnacle of a universe built for us. We are the transient, fortunate inhabitants of one possible world among a near infinity of others, our particular broken symmetries serving as the unique signature of our cosmic address, a fingerprint of chance that made observation and wonder possible. These grand ideas are not just philosophy, they are predictions waiting for a verdict, To test the story of broken symmetry, we must build time machines not of metal and gears, but of steel, superconducting magnets, and pure human ingenuity. Our most powerful window into the primordial past is the Large Hadron Collider, a 27-kilometer ring buried deep beneath the border of France and Switzerland. Inside its circular tunnel, protons are accelerated to within a whisper of light speed and then smashed together head-on. These collisions, happening hundreds of millions of times per second, recreate for a fleeting instant the conditions of the universe when it was less than a trillionth of a second old. In that microscopic fireball, temperatures soar to over 10 trillion degrees, and energy condenses back into particles that have not roamed freely since the cosmos began. The goal is to sift through the resulting debris for something new, something unexpected, a clue to the deeper layers of reality. The Collider's crowning achievement was the discovery of the Higgs boson in 2012. Detecting this particle was like finding the signature of the cosmic field that gives everything mass, a direct confirmation of the electroweak symmetry break. But the hunt is far from over. The same detectors' monumental experiments named ATLAS and CMS are now searching for the fingerprints of even grander symmetries. They look for the missing energy that could signal an invisible particle, a candidate for dark matter. They search for the unusual decay patterns or unexpected particles that could be the superpartners predicted by supersymmetry. Every anomaly in the data, every statistical bump is scrutinized, for it could be the first glimpse of the physics that governed the universe's first, most symmetric moments. But our cosmic detective work is not confined to one machine. Symmetry breaks leave their signatures in many forms, and science has developed a whole toolkit to hunt for them. Precision is just as powerful as power. In laboratories around the world, physicists conduct exquisitely sensitive experiments on well-known particles, watching them decay with atomic clock precision. By comparing the decay rates of particles and their antimatter counterparts, like B mesons or kaons, they measure the exact degree of CP violation, that subtle cosmic bias between matter and antimatter. These experiments are listening for a wrong note in a symphony played perfectly a billion times, refining our understanding of the asymmetry that saved the universe from oblivion. Meanwhile, in vast tanks of ultra-pure water or liquid argon buried under mountains, neutrino observatories watch for the ghostly metamorphosis of these particles as they arrive from the sun or from distant cosmic accelerators. Each oscillation from one flavor to another is a direct measure of their tiny, non-zero masses, a living testament to broken symmetry in the neutrino sector. And on an entirely different frontier, gravitational wave observatories like LIGO and Virgo have opened an entirely new sense. They are listening to the ripples in spacetime itself. While they have so far heard the mergers of black holes and neutron stars, their ultimate sensitivity might one day detect the faint, persistent hum from the violent phase transitions of the early universe, or even the catastrophic snap of a cosmic string vibrating across the cosmos. That would be a direct recording of the universe's symmetry-breaking moments, a soundtrack from creation. Each of these efforts, from the colossal to the precise, represents a strand in a single, profound human endeavor. We are translating the universe's metaphysical choices into measurable data. The particle collider, the underground tank, the laser interferometer, they are all extensions of our curiosity, tools for cosmic archaeology. They allow us to probe energies and epochs we can never visit, testing whether our elegant mathematical stories about symmetry and its breaking are true descriptions of reality or beautiful fictions. Every null result, every expected particle not found, is not a failure but a guidepost. It tells us the universe is not that way, forcing our theories to evolve, to become more resilient, or perhaps to surrender to a more astonishing truth. This experimental frontier is where our grandest cosmic narratives meet the unyielding rigor of reality. It is a slow, collective, and glorious attempt to read the blueprint of existence, one shattered symmetry at a time. The equations that describe our universe are not merely tools for calculation, they are works of art. For centuries, the greatest minds in physics have been guided by a profound aesthetic intuition, a conviction that the fundamental laws of nature must possess a certain elegance and symmetry. This is not a modern whim, it is an ancient pursuit. The Greek philosophers saw geometric perfection in the heavens, believing the planets moved in perfect circles because that shape was the most beautiful and symmetrical. While their specific model was wrong, their instinct was not. That drive for harmony echoes through the ages, finding its purest expression in the language of mathematics. The physicist Paul Dirac, whose equation predicted the existence of antimatter, famously stated, "It is more important to have beauty in one's equations than to have them fit experiment." To the outsider, this might sound like reckless idealism, placing artistry above evidence. But to a theoretical physicist, mathematical beauty is a compass. It points toward truth. A clunky, ad hoc equation that fits today's data but lacks grace is often seen as incomplete, a temporary patch hiding a deeper, more symmetrical law. Dirac's own work is the ultimate testament. His equation, crafted for its mathematical elegance and symmetry, demanded the existence of a particle with the same mass as the electron but opposite charge. At the time, no such thing was known. It was an aesthetic prediction, and yet it was correct. The discovery of the positron, the first piece of antimatter, was a triumph not just of science but of a beautiful idea. This aesthetic drive propelled Einstein as he sought a unified field theory, and it fuels the quest for supersymmetry and strings today. We are drawn to symmetrical laws because they feel inevitable, necessary, and true. But here lies the exquisite tension. The universe, in its ultimate creative act, did not remain in that state of perfect, sterile beauty. It broke its own symmetries. And in doing so, it traded a single, flawless equation for the breathtaking, messy diversity of the world we see. The beauty we find in a snowflake, a spiral galaxy, or the double helix of Dine is not the beauty of perfect, unchanging symmetry. It is the beauty of symmetry broken in a specific, fruitful way. It is the beauty of a theme and variation. The underlying laws may be elegant and symmetric, but their application, their manifestation in the cold reality of an expanding cosmos, generates complexity. This is the philosophical heart of our journey. The story of cosmic symmetry breaking is more than a physics lesson. It is a deeply human narrative. It speaks to our own longing for order and perfection, and our simultaneous celebration of the unique, the flawed, and the emergent. We strive for perfect equations, yet we live in a world built from their carefully orchestrated failure. The universe seems to tell us that true creativity, true richness, requires a departure from the ideal. From a single, symmetric origin, we get particles with mass and forces with character. From a uniform sea of energy, we get stars, planets, and life. The most beautiful outcome is not the pristine starting point, but the magnificent structure that grows from its deliberate imperfection. Our quest to understand the cosmos, then, is a dance between two kinds of beauty, the abstract elegance of the laws and the tangible splendor of their broken, creative consequences. The universe's first great act of symmetry breaking left behind a silent, invisible signature. That initial burst of inflation smoothed the cosmos to an astonishing degree, but it did not create a perfect, featureless void. Instead, it took the faintest quantum jitters, the inherent uncertainty of existence at the smallest scale, and stretched them across the entire sky. These were the tiniest possible breaks in perfect homogeneity, microscopic ripples in density where, by random chance, a few more virtual particles flickered into being here than there. In that searing dawn, these fluctuations were frozen into the fabric of space-time as subtle variations in the gravitational field. They were the universe's first and most important imperfections, the seeds from which all structure would grow. For hundreds of millions of years, these seeds lay dormant in a cosmos that was still too hot and energetic for gravity to get a grip. The universe was a glowing, opaque fog of plasma, where light and matter were locked in a constant struggle. But then, everything changed. As expansion continued to cool the cosmos, electrons and protons finally combined to form neutral hydrogen atoms in an event called recombination. Suddenly, the fog cleared. Light, which had been bouncing around for eons, was set free on a straight path. That first flash of liberated light is what we now detect as the cosmic microwave background radiation. And when we map its temperature across the sky with incredible precision, we are looking at a baby picture of the universe, only 380,000 years old. And there, imprinted on that ancient light, we see them, the very seeds themselves. The temperature of the background is not perfectly uniform. It shows minuscule variations, hot spots and cold spots that differ by only about 1 part in 100,000. These tiny patterns are the direct imprint of those primordial density fluctuations, the gravitational blueprint for everything to come. This was the universe's symmetry on the largest scale, its smoothness, broken in the gentlest possible way. Gravity now had a map to work with. Over the next billion years, it began its slow, relentless sculpting. Regions of space that were ever so slightly denser had a bit more gravitational pull. They began to draw in the sparse hydrogen gas from their surroundings. As more matter fell in, the gravitational pull increased, drawing in even more. This is a process called gravitational instability, a powerful positive feedback loop where small advantages compound over cosmic time. The first structures to form were likely vast, dark filaments of gas, tracing out a cosmic web in 3 dimensions. At the intersections of these filaments, where the density was highest, the first protogalactic clouds coalesced. Inside these clouds, smaller knots collapsed further, igniting as the first generation of stars, monstrously large and brilliant, flooding the young universe with its first true light. This epoch of cosmic dawn is now being glimpsed by the James Webb Space Telescope, which peers back to see the faint, reddened glow of those earliest galaxies, verifying the predictions of our models. The growth did not stop there. Galaxies, drawn together by their mutual gravity, began to cluster. They merged and cannibalized each other, growing from small, irregular blobs into the majestic spirals and ellipticals we see today. The voids between the filaments, regions that started with a slight underdensity, were emptied further, becoming the vast, dark deserts that separate the bright cities of galaxies. This entire grand architecture, from the largest supercluster to the smallest dwarf galaxy, is a direct consequence of those initial quantum seeds. It is a fossil record, but not one written in stone. It is written in the distribution of matter across billions of light years. When astronomers create immense 3-dimensional maps of the universe, plotting the positions of millions of galaxies, they see the ghostly outline of that primordial web. Supercomputer simulations that start with the fluctuations seen in the cosmic microwave background, and then let gravity work for 13.8 billion years reproduce, with stunning accuracy, the cosmic structures we observe. This is one of the most profound validations of our entire cosmic story. It connects the quantum mechanical uncertainty of a subatomic moment to the gravitational majesty of a galactic supercluster. The symmetry of a perfectly smooth universe had to break for anything interesting to exist, and it broke in a very specific way, leaving a pattern so subtle it required the most powerful telescopes and computers in history to decode. That pattern, grown to cosmic proportions, is the universe we call home, a breathtaking tapestry woven from the threads of broken perfection. But the most intimate symmetry break of all may not be in the cosmos, but in the act of looking at it. Deep within the quantum rules that govern particles, there lies a profound and unsettling mystery. A single electron left unobserved does not have a definite position or spin. It exists in a shimmering haze of all possible states at once, a perfect symmetry of potential called a superposition. It is only when we measure it, when we ask it a specific question with our detector, that this symmetry violently shatters. The electron snaps into a single, definite answer. This sudden transition from everything possible to one thing real is the measurement problem, and it suggests that the act of observation itself might be the ultimate symmetry-breaking event. Why should looking at something force it to make a choice? The most famous answer is the Copenhagen interpretation, championed by pioneers like Niels Bohr. It draws a sharp line between the quantum world of probabilities and the classical world of definite outcomes. In this view, the measuring apparatus, and by extension the conscious observer, is not part of the quantum system. It exists outside, and its interaction causes the wave function, the mathematical description of all possibilities, to collapse. The symmetry of superposition breaks because our classical tools cannot handle ambiguity. They are designed to give one answer, and so the universe obliges, but this has always felt unsatisfying, like a rule that says magic happens here. It places consciousness or classicality on a mysterious pedestal. An alternative, the many worlds interpretation, offers a breathtakingly different solution. It proposes that the symmetry never actually breaks. Instead, when a measurement is made, the universe itself splits. Every possible outcome of the quantum superposition becomes real in a newly branched parallel reality. In one world, the electron spins up. In another, perfectly real and separate world, it spins down. There is no collapse, only an ever-branching tree of possibilities where every quantum dice roll lands on every number simultaneously. In this picture, we are not breaking a symmetry, we are simply following one path on an infinite fractal tree. Our perception of a single, definite outcome is just a local illusion, a consequence of our consciousness being trapped on a single branch. Then there are theories that seek a physical mechanism for collapse. Objective collapse models suggest that superposition is inherently unstable. Perhaps when a quantum system becomes too large or massive, its own gravity, as suggested by Roger Penrose, causes it to spontaneously pick a state. In this idea, gravity is not just a force, but the universe's way of insisting on a single reality at large scales. It is a built-in asymmetry that emerges from the interplay of quantum theory and general relativity. Others look to the arrow of time itself, wondering if the irreversible flow from past to future provides the directionality needed for collapse. Each interpretation is a different story about how and why the quantum symphony of possibilities resolves into the single note of our experience. They all grapple with the same core idea that knowledge comes at a cost. To learn something definite about the universe, we must force it to sacrifice its quantum wholeness. This transforms observation from a passive act of reception into an active act of creation. When you look at the moon in a very real sense, you are not just seeing it, you are compelling a vast collection of quantum particles to settle into the specific arrangement you call the moon. Your consciousness or your instrument is not a camera recording a pre-existing scene. It is a participant in a cosmic dance, one that choreographs reality out of a fog of potential. This ties the microscopic puzzle directly to our lived reality. The definite world of tables, chairs, and stars is not the primary reality. It is the product of countless trillions of quantum symmetry breaks, happening every instant, crystallized by the relentless process of interaction and observation. Our classical universe of cause and effect emerges from this deeper, stranger quantum layer. much like the broken symmetries of the early cosmos gave rise to forces and matter. The measurement problem asks us to consider that the very fabric of the definite present is being woven, thread by thread, from the symmetric possibilities of the quantum past, and that we, the observers, are holding the needle. This quantum connection that defies space hints at a symmetry far stranger than any we have yet encountered. It is not a symmetry of shape or force, but a symmetry of information, an invisible thread tying the fates of particles together across the cosmos. This is quantum entanglement. To understand it, picture a single particle decaying into two. According to quantum law, these two offspring are born in a single, shared quantum state. They are like a pair of magical dice created together so that their spins are perfectly linked. If one die shows up, the other must show down, and this correlation is set in stone from the moment of their birth. The astonishing part is what happens when you separate them. You could send one die to the far side of the galaxy and the other to a lab on Earth. The moment you look at the Earth-bound die and see it land on up, its twin, billions of light years away, instantly becomes down. This connection seems to happen faster than light, a notion that troubled Einstein, who famously called it spooky action at a distance. He believed there must be a simpler explanation, that perhaps each particle carried a hidden set of instructions, like a secret code, determining its outcome from the start. These were the local hidden variables, a way to preserve a sensible, local reality where influences cannot travel faster than light. For decades, this was a philosophical debate. Then, in the 1960s, the physicist John Bell devised a brilliant theorem. He showed that if local hidden variables were real, then certain statistical correlations between measurements on entangled particles could never exceed a specific limit. It was a testable prediction. If experiments showed correlations stronger than Bell's limit, then local realism, the idea that particles have definite properties before we measure them and that influences are local, would be false. The universe would be genuinely spooky. The experiments began most famously by Alain Aspect and his team in the 1980s. They were meticulous, closing potential loopholes. The result was clear and revolutionary. The quantum correlations violated Bell's inequality. The particles were not following secret, pre-written scripts. Their connection was real, non-local, and instantaneous. This confirmed that entanglement is not just a mathematical quirk, it is a fundamental feature of reality. The symmetry here is one of perfect correlation. It is as if the two particles are not two separate objects at all, but two aspects of a single, unified system, no matter how vast the physical distance between them. This broken locality has become the bedrock of a new technological revolution. In quantum cryptography, entangled particles can create unbreakable codes because any attempt to eavesdrop on their communication disturbs their delicate linked state, alerting the users. In quantum computing, entanglement is the resource that allows qubits to perform calculations in parallel across a vast landscape of possibilities, promising to solve problems that would take classical computers millennia. But the role of entanglement may reach far beyond our labs, into the cosmic past. Some cosmologists now speculate that the infant universe was in a state of near-total entanglement. Every particle, every field, was linked to every other in a dense web of quantum connections. Then came inflation, that violent stretching of space-time. As the universe expanded exponentially, these threads of correlation were stretched and diluted. The intense, unified quantum state of the beginning was pulled apart into the mostly classical, separable universe we see today. In this view, the cosmic microwave background, that snapshot of the early cosmos, might still hold subtle statistical signatures of that primordial entanglement, a ghostly imprint of a time when everything was intimately connected to everything else. Entanglement, therefore, represents a different kind of foundational symmetry, It is not about invariance under change, but about the inseparability of a whole. It is a reminder that at its most fundamental level, the universe may not be a collection of isolated things, but a single, correlated system whose apparent separateness is an illusion born of expansion and time. This non-local thread, woven into the quantum fabric, may have been one of the first and most profound symmetries of all, a hidden unity that quietly guided the evolution of the cosmos from a single quantum state to the vast, structured reality we now explore. That ghostly energy of the void is not a static background hum, but a ceaseless, turbulent sea. Its existence is a direct command from one of quantum theory's most fundamental rules, the Heisenberg uncertainty principle. This principle tells us that certain pairs of properties, like a particle's position and its momentum, cannot both be known with perfect precision at the same time. The more you pin down one, the more the other becomes a blur of possibility. This inherent fuzziness applies not just to particles, but to the fields that fill all of space. Even in a perfect vacuum, at a temperature of absolute zero, a field cannot sit perfectly still at zero energy. To do so would be to declare both its value and its rate of change with infinite certainty, which the universe forbids. Instead, every quantum field is compelled to jitter, to fluctuate around a minimum value. This minimum energy is the zero-point energy, and it means that what we call empty space is in fact a vibrant quantum foam, a frenzy of virtual particle-antiparticle pairs flickering into and out of existence on borrowed energy and borrowed time. This is not a metaphor, it is a mathematical prediction so robust that we see its effects in the lab. Place two perfectly smooth, neutral metal plates extremely close together in a vacuum. The ceaseless fluctuations of the electromagnetic field between them are restricted, while those on the outside are not. This creates a subtle pressure difference that actually pushes the plates together, an experimental fact known as the Casimir effect. It is a direct, measurable whisper of the vacuum's hidden energy. But here the mathematics leads us into a terrifying abyss. When physicists attempt to calculate the total zero-point energy density of all quantum fields, they sum up the contributions from every possible wavelength, from the largest scales down to the infinitesimally small Planck length. The result is an infinite number, a nonsensical answer that screams our theories are incomplete. To make progress, they use a brilliant mathematical technique called renormalization. Think of it as a cosmic accounting trick. You acknowledge that the raw calculation gives infinity, but you then carefully subtract other infinite quantities that arise from the mass and charge of particles, leaving behind a finite, measurable remainder that matches experiment. It is a procedure of breathtaking elegance and utility, the reason we can make such stunningly accurate predictions in particle physics. Yet for the vacuum energy, this process fails catastrophically. Even after renormalization, the estimated finite value for the energy density of empty space is around 1 followed by 120 zeros larger than the tiny, positive value we actually observe from the accelerating expansion of the cosmos. This is not a small error. It is the largest discrepancy between theory and observation in all of science, the vacuum catastrophe. It tells us that something is profoundly wrong or profoundly hidden. The implication is staggering. It suggests there must exist a symmetry, a perfect cancellation mechanism that zeroes out 120 orders of magnitude of quantum vacuum energy. But then, that symmetry itself must be broken by the tiniest, most inexplicable amount, leaving behind the faintest positive residue we call dark energy. This means the vacuum state of our universe, the very definition of nothingness, is not the symmetric, featureless baseline we assumed. It is a very specific, finely tuned, broken state. The void has a texture, a preferred energy level. It chose this particular value from a near-infinite landscape of possibilities. Understanding why this specific nothing is our reality may require more than a new particle or a new field. It may demand a revolution in our understanding of quantum gravity, a theory that tells us what happens to spacetime itself at those unimaginably small scales where the zero-point energy is born. The vacuum catastrophe is not just a technical puzzle, it is a direct challenge to our concept of emptiness, asking us what it truly means for something to be nothing at all. But the Higgs field, for all its success, is not the only possible answer. The mechanism that gave particles their mass is a triumph of the Standard Model, yet its elegance comes with unanswered questions that have inspired physicists to dream of entirely different worlds. One of the most radical and compelling alternatives is known as Technicolor. In this vision, the Higgs boson is not a fundamental, elementary particle at all. It is a composite object, a bound state of something entirely new. Just as a proton is not fundamental but made of quarks held together by the strong nuclear force, a Technicolor Higgs would be made of new constituents called technoquarks, bound by a new, powerful force. This idea transplants the logic of the strong force into the heart of electroweak symmetry breaking. In our world, the strong force's tendency to bind quarks together, a phenomenon called confinement, leads to the formation of protons and neutrons. In a Technicolor universe, a similar but separate force acts on technoquarks. As the universe cooled, this new strong interaction would naturally cause technoquarks to condense into composite particles, and this condensation itself would break the electroweak symmetry, giving mass to the W and Z bosons without requiring a fundamental Higgs field. It is a beautifully economical idea, using a known principle from one part of physics to solve a mystery in another. The Higgs boson in this picture would be analogous not to a new fundamental building block, but to a particle like the pion in nuclear physics, a composite messenger of the binding force. This approach promised to solve some of the aesthetic unease with the Standard Model Higgs, particularly the hierarchy problem, by replacing a delicate elementary scalar particle with the robust dynamics of a strong force. For a time, it was a leading contender for how our universe might truly work, yet nature, as revealed by our most powerful experiments, had other plans. The discovery of the Higgs boson at the Large Hadron Collider was a milestone, but the particle's properties were the real test. The measured mass of the Higgs, around 125 billion electron volts, and the way it interacts with other particles match the predictions of a fundamental Higgs field with striking precision. This has placed severe constraints on Technicolor models. Most simple versions predicted a spectrum of new composite particles, partners to the Higgs, that should have been within the energy reach of the collider. Their absence is a strong hint that the universe did not choose this particular path. Furthermore, precision measurements of the weak force over decades had already created a tight web of expectations, a net that many Technicolor scenarios struggled to fit through without becoming overly complicated. This does not mean the idea is dead, but it has been pushed to a more complex and subtle form, often blended with other concepts like walking Technicolor, where the force's strength changes with energy scale in a very specific way. Exploring these alternatives is far from a futile exercise. It highlights the incredible creativity and rigor of theoretical physics. Scientists do not simply settle on the first nice idea. They invent entire universes of possibility and then relentlessly test them against reality. The story of Technicolor versus the Higgs mechanism is a masterclass in that process. It reminds us that our current standard model, for all its predictive power, may be just one effective description, one manifestation of a deeper and perhaps more symmetrical truth. The fact that the simple, elegant Higgs field fits the data so well is a tremendous victory. But the continued search for alternatives, for composite Higgses or extra dimensions or supersymmetry, is driven by a profound intuition that the final answer should feel inevitable, not finely tuned. The true mechanism behind mass and symmetry breaking Whether it is the Higgs we have found or something more exotic waiting in the next energy frontier, ultimately holds the key to why the universe has the substance and structure that allows us to ask the question in the first place. Our cosmic map of the primordial universe contains a feature so unsettling that scientists gave it a dramatic name, the axis of evil. This is not a galactic menace, but a mysterious pattern etched into the oldest light we can see. The cosmic microwave background, that faint whisper from the universe's infancy, is remarkably uniform, but it is painted with tiny temperature variations, the seeds of all future galaxies. According to our fundamental principles, these hot and cold spots should be distributed randomly with no preferred direction, a concept known as statistical isotropy. The cosmos should look the same in every direction on the largest scales. Yet, when researchers from the WMAP and later the Planck satellite missions analyzed their exquisite maps, they noticed something strange. Certain large-scale patterns in the temperature fluctuations, features spanning billions of light-years, appeared to be subtly aligned with the plane of our own solar system. It is as if the universe's first brushstrokes were painted with a faint reference to our local celestial neighborhood, a correlation that should be astronomically impossible. The chance of such an alignment happening randomly is incredibly small, suggesting the pattern might be real. This potential discovery strikes at the heart of cosmology's most cherished assumptions. The principle of isotropy, that the universe has no center and no preferred direction, is a cornerstone of the Big Bang model and of Einstein's cosmological principle. It is the reason we can assume the laws of physics are the same everywhere. The axis of evil, if it is not a statistical illusion or an artifact of how we process the data, would imply that on the grandest scales, the universe is not perfectly symmetric. It would have a preferred axis, a cosmic north, breaking the symmetry of isotropy and suggesting our place in the cosmos might not be entirely ordinary. The debate within the scientific community is intense and ongoing. Skeptics argue powerfully that the anomaly could be a trick of the light, a consequence of foreground contamination from our own Milky Way galaxy, or a subtle systematic error in the incredibly complex data analysis. The Planck mission, with its unprecedented sensitivity, was meant to resolve the issue. While it confirmed some of the unusual large-scale features, it did not provide a definitive answer, leaving the mystery in a tantalizing state of uncertainty. The implications, however, are too profound to ignore. If the universe truly has a preferred axis, it would force a radical reconsideration of our cosmic origin story. The theory of inflation, which explains the universe's large-scale smoothness, might need revision. Perhaps the inflationary field itself had a directional quality, stretching space more in one direction than another. Or perhaps we are seeing the imprint of something even more fundamental, a pre-inflationary universe with a structure we cannot yet imagine. The axis of evil serves as a powerful, humbling reminder. Just when we think we have mapped the cosmos and understood its symmetric foundations, the universe presents us with a cryptic clue written in its first light. It whispers that our grandest theories might be approximations, and that the ultimate architecture of reality could contain asymmetries as deep and mysterious as the ones that gave us matter and time. This anomaly is not a flaw in the data, but a potential doorway challenging us to look deeper and wonder if the cosmos, in its infinite grandeur, still holds a sense of direction we have only begun to perceive. The idea that our universe is not alone emerges almost inevitably from the mathematics of its own birth. When we trace the logic of cosmic inflation, that super-fast stretching of space, to its ultimate conclusion, we are led to a staggering possibility. Inflation may not be a single event that started and stopped in our past. Instead, it could be eternal, a ceaseless, self-replicating process. In this view, the vacuum of space is not a single, stable state. but a landscape of possibilities, with different regions possessing different amounts of inherent energy. Think of it like a vast cosmic mountain range, with peaks and valleys representing different possible configurations of reality. Our universe began when a tiny patch of this landscape, perched on a high-energy peak, became unstable. It rolled down into a lower-energy valley, releasing its pent-up energy as the heat and particles of our Big Bang. But here is the key: in an eternally inflating cosmos, this process never ends. While our pocket of space transitioned to a low-energy state and stopped inflating, giving rise to galaxies and stars, the overarching inflationary space continues to expand at a blistering rate. Within that still inflating sea, quantum fluctuations can constantly kick new patches over the edge, sending them tumbling into their own valleys, each one a new Big Bang, a new bubble universe. This is the theory of eternal inflation, and it paints a picture of a meta-cosmos, a frothing foam of universes, each with its own distinct physics, forever being born. Our entire observable cosmos, with all its hundreds of billions of galaxies, is just one bubble in an infinite, ever-growing foam. This transforms the deepest questions of existence. We no longer need to ask why the Higgs field settled into the precise value that gives particles their mass in our universe. We simply ask, in which valley did our bubble form? The specific broken symmetries that gave us electromagnetism, the weak force, and the particles we know are not universal laws. They are local bylaws, the unique environmental conditions of our particular cosmic neighborhood. This perspective finds a powerful echo in another grand theory, string theory. As we discussed, string theory suggests the fundamental ingredients of reality are tiny, vibrating strings, and it requires extra spatial dimensions to maintain its mathematical harmony. But how are those extra dimensions curled up? The theory does not predict a single, unique shape. Instead, there is a colossal landscape of possible configurations, perhaps 10 to the 500 different ways to compactify those dimensions. Each distinct shape in this landscape corresponds to a different set of physical laws, different particle masses, and different strengths for the fundamental forces. In essence, each shape defines a different possible universe with its own pattern of symmetry breaking. So we have two powerful yet speculative ideas converging. Eternal inflation provides the engine for creating countless bubble universes. The string theory landscape provides the menu of possible physics each bubble could have. Together, they form the conceptual framework for a multiverse, an ensemble of realities where the constants of nature are not fine-tuned by design, but randomly distributed. In this vast statistical ensemble, most bubbles are stillborn. Their vacuum energy is too high, ripping space-time apart instantly. Their forces are too weak to bind atoms or too strong to allow for complex chemistry. They are cosmic deserts, silent and unobserved, but in a vanishingly small fraction of bubbles by pure chance, the numbers fall within the narrow window that allows for atoms, stars, planets, and the emergence of complexity. We, of course, find ourselves in one of those rare, fruitful bubbles. Our existence is not a clue to a grand, singular design, but a statistical inevitability. We are the inhabitants of a universe that won the cosmic lottery. This framework fundamentally reframes the mystery of our broken symmetries. It shifts the question from why did symmetry break this exact way, to what does our observation tell us about the landscape of all possible breaks. The weakness of gravity, the specific masses of particles, the tiny value of the cosmological constant, these are not fundamental truths of all reality. They are local environmental conditions, the unique signature of our cosmic address. The multiverse idea is without question controversial. Its most significant challenge is testability. By definition, other bubble universes are causally disconnected from our own, hidden beyond our cosmic horizon. We may never receive a signal from a neighboring bubble. Yet, scientists are creatively searching for indirect signatures. Could the violent collisions between expanding bubble walls in the early cosmos have left an imprint on the cosmic microwave background, a kind of bruise on the sky? Could the specific pattern of gravitational waves from the universe's first moments reveal clues about the shape of the landscape? These are extraordinarily difficult measurements, but they represent the frontier of turning a profound philosophical concept into an empirical science. Whether the multiverse is a physical reality or a useful metaphor, it serves a crucial purpose. It provides a conceptual container for the apparent fine-tuning we see everywhere. It suggests that symmetry breaking is not a unique, singular event in one cosmos, but a variable outcome across a meta-reality of unimaginable scale. Our particular slice of existence, with its specific broken rules that allow for galaxies and life, is just one note in an infinite symphony of possibilities, most of which play to an empty hall. Black holes are the ultimate paradox, a place where the universe's most cherished symmetries are stretched to the breaking point. At the heart of this crisis lies a single, deceptively simple question. What happens to the story of an object when it crosses the point of no return? According to the elegant symmetry of quantum mechanics, information can never be truly destroyed. It can be scrambled, encoded, or hidden, but the complete history of a particle, its quantum state, must be preserved. This principle of unitarity is a sacred symmetry, ensuring the evolution of the universe is predictable and reversible in theory. Yet, the classical picture of a black hole, born from Einstein's general relativity, paints a starkly different scene. An object falls in, passes the event horizon, and is crushed into the singularity at the center. From the perspective of the outside universe, that object is gone, its information seemingly erased from existence. The paradox deepens with Stephen Hawking's revolutionary insight. Black holes are not perfectly black. Due to quantum effects near the event horizon, they slowly leak a faint glow of thermal radiation, losing mass until they potentially evaporate completely. Hawking's calculations suggested this radiation was purely random, carrying no information about what fell in. If a black hole evaporates into a featureless cloud of photons, then the information about the star that formed it, the book you threw in, the very history of its contents, is lost forever. This is the information paradox, a direct conflict between two pillars of physics. The unitary symmetry of quantum mechanics demands preservation, while the grim geometry of black holes suggests ultimate erasure. For decades, this stood as perhaps the most severe challenge in theoretical physics, a sign that our understanding of reality was incomplete at its most extreme frontier. The path to a solution may lie in reimagining the very nature of the event horizon. It is not a one-way membrane to oblivion, but a dynamic quantum surface buzzing with incredible activity. This is the heart of the holographic principle, one of the most profound ideas to emerge from the struggle with the paradox. It proposes that all the information describing everything within a volume of space can be perfectly encoded on its boundary, a lower dimensional surface. For a black hole, this boundary is its event horizon. Think of it like a cosmic thumb drive. When an object falls into a black hole, its information is not lost inside. Instead, it is scrambled and imprinted onto the quantum fabric of the horizon itself, much like the data of a three-dimensional movie is stored on a two-dimensional Blu-ray disc. The three-dimensional interior, with all its apparent depth, is a projection of that two-dimensional data. This means the information never actually enters a place from which it cannot escape. It is painted on the surface pixel by quantum pixel. The entropy of a black hole, a measure of its hidden information, supports this stunningly. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was the first major clue that the true degrees of freedom, the bits of information that describe the black hole, reside on its surface. Later work, most notably by Juan Maldacena in the late 1990s, provided a concrete mathematical framework for this holographic duality, showing a direct equivalence between a gravitational theory in a volume and a quantum field theory on its boundary. The black hole's interior, in this view, is a kind of emergent illusion, a useful story generated by the complex interactions of quantum data on the horizon's surface. If information is stored on the horizon, then how does it eventually escape during evaporation? The answer may involve a subtle but critical correction to Hawking's original picture. Modern research suggests that Hawking radiation is not completely random and thermal. Due to the intricate quantum entanglement between particles just inside and just outside the horizon, the radiation leaking away carries with it tiny, encrypted traces of the information imprinted on the surface. The process is extraordinarily complex, like burning an encyclopedia and trying to read its contents in the patterns of the rising smoke and ash. The information is there, but it is transformed beyond easy recognition. This gradual quantum mechanical leakage means that by the time the black hole has fully evaporated, the information has, in principle, been returned to the universe. The paradox dissolves if we accept that the event horizon is not a passive wall but an active, information-processing membrane. This resolution, however, comes at a profound cost to our classical intuition. It demands that we abandon the idea of a smooth, continuous spacetime that exists independently inside the black hole. The dramatic principle of locality, that objects interact only with their immediate surroundings, must break down in the presence of such intense gravity. An object falling in and its information being encoded on the horizon are two descriptions of the same event, seen from different quantum perspectives. This forces a radical reconsideration of symmetry itself at the Planck scale. The familiar symmetries of spacetime, like rotation or translation, may be emergent properties of a deeper, non-local quantum system where information and entanglement are the fundamental currency. The black hole, therefore, is not a destroyer of symmetry but a teacher. It shows us that the most fundamental symmetries of the universe may not be about the geometry of space, but about the preservation of quantum information, a deeper, more abstract law from which even gravity and spacetime themselves are born. The cosmic story of broken perfection is not confined to the physics of the early universe. It echoes through the very fabric of human experience, offering a profound metaphor for how creativity, evolution, and change actually work. In art, perfect symmetry can feel static, even sterile. A face drawn with absolute mirror precision is uncanny, lacking life. True artistic power often arrives in the deliberate break, the slight asymmetry in a sculpture's pose, the unexpected brushstroke that disrupts a pattern, or the dissonant chord that resolves into something new. These are not mistakes, they are the artist's version of a cosmic phase transition, introducing a tension that creates interest, movement, and emotional depth. The universe itself seems to follow this same creative principle, trading a state of flawless, featureless unity for a world rich with texture, contrast, and story. This principle is woven into the biology of our own bodies. Consider the human heart positioned slightly left of center. This elegant asymmetry is not an error, it is a functional necessity for efficient circulation. Our brain hemispheres are specialized, with language often residing more in one side and spatial awareness in the other. This lateralization allows for a more complex and capable mind than a perfectly symmetrical brain could achieve. Even at the molecular level, the uniform handedness of life's building blocks, that homochirality we discussed, is a biological symmetry break that was essential for the rise of complex organisms. Evolution itself is a grand engine of symmetry breaking. It operates on variation, on deviations from the norm. A genetic mutation is a break in the symmetrical replication of DNA, and while most such breaks are neutral or harmful, a rare few open doors to new functions, new forms, and ultimately new species. Without this capacity to break established patterns, life would be frozen in a single, perfect, and extinct form. Philosophers across cultures and millennia have wrestled with a fundamental puzzle: the relationship between the one and the many. How does boundless diversity arise from a single source? The story of cosmic symmetry breaking provides a breathtakingly concrete narrative for this ancient question. The universe began as the ultimate one, a state of perfect, undifferentiated unity. Then, through a cascade of spontaneous choices as it cooled, it fractured into the many, the four forces, the particles with mass, the galaxies and stars. The one did not vanish, it transformed. Its underlying symmetric laws remain, but they now manifest in the spectacularly diverse and asymmetric reality we inhabit. This scientific insight reframes our understanding of imperfection. The cracks in the cosmic crystal are not evidence of a flawed design or a fall from grace. They are the birthplace of everything interesting, complex, and beautiful. In our own lives and societies, we see this pattern constantly. Innovation rarely comes from perfectly following a rulebook. It emerges when someone asks a different question, takes a path less traveled, or combines ideas in a novel way. It is a symmetry break. Cultural evolution thrives on the introduction of new stories, new technologies, and new perspectives that challenge the established order. These moments of disruption can be uncomfortable, even frightening, much like the universe's phase transitions were likely violent and turbulent. Yet, they are the necessary precursors to growth and new forms of stability. The journey from a symmetric origin to an asymmetric reality teaches us that deviation from perfection is not a flaw to be lamented, but the fundamental mechanism of creation itself. Our entire existence, from the atoms in our cells to the cultures we build, is a testament to the creative power of broken symmetry, a reminder that the most profound beauty often lies not in perfect stillness, but in the dynamic, evolving patterns that emerge when things choose to be different. The blueprint of the cosmos is still missing its final pages, and the next generation of explorers is already building the tools to read them. Our story of broken symmetry is not a closed book, but a living mystery, and the coming decades promise experiments of breathtaking scale and sensitivity designed to catch the universe in the act of revealing its deepest secrets. On the ground, plans are underway for a machine that dwarfs even the Large Hadron Collider, the proposed future circular collider. This behemoth, with a tunnel 100 kilometers in circumference, would smash particles together with energies up to 10 times greater than today's limits. Its goal is to scrutinize the Higgs boson with microscopic precision, hunting for any subtle deviation from the standard model's predictions that could signal new particles or hidden dimensions. It aims to recreate conditions a fraction of a second closer to the Big Bang itself, potentially allowing us to witness the next layer of symmetry unification, where the electromagnetic, weak, and strong forces might merge into one. Meanwhile, the hunt for dark matter is entering an era of profound quiet. Next-generation detectors, using ever-purer materials and placed in even deeper underground sanctuaries, will listen with almost unimaginable sensitivity for the faintest tick of a wimp or the whisper of an action, another theoretical dark matter candidate. Their success would not just identify the universe's missing mass, it would open a portal to an entire hidden sector of physics, a shadow realm governed by symmetries untouched since the beginning. The view from space will be equally revolutionary. The Laser Interferometer Space Antenna, or LISA, is a mission that will turn the heavens into a gravitational wave observatory. Consisting of 3 spacecraft flying in a perfect triangle millions of kilometers apart, it will detect ripples in spacetime at frequencies too low for ground-based instruments. Lisa could hear the cosmic symphony of merging supermassive black holes, but more tantalizingly, it might capture the faint, persistent hum from the universe's violent phase transitions. It could listen directly for the popping of cosmic bubbles or the vibrating snap of a cosmic string from the epoch of inflation, offering a soundtrack to the very symmetry-breaking events we have only theorized. Closer to home, next-generation telescopes mapping the cosmic microwave background with even finer detail will search for the twisted patterns of primordial gravitational waves or the statistical fingerprints of primordial entanglement, looking for the subtle scars left on the infant universe's face. Theoretical physicists are not waiting idly for this data. They are forging new mathematical languages to interpret what we might find. Some are exploring stunningly beautiful objects like the amplituhedron, a geometric shape whose volume directly calculates the outcomes of particle collisions. This approach bypasses the traditional framework of quantum fields and spacetime, suggesting that this grand tapestry of existence, from the quantum foam to the galactic web, is woven from a single, recurring thread. The universe began not with a chaotic explosion, but with a silent, perfect unity, a state of supreme symmetry where every force was one and every particle was identical. That initial condition was the ultimate blank canvas, a realm of pure potential governed by a single, elegant law. But potential alone cannot create a world. For the universe to become something, for it to have texture, history, and life, that perfect symmetry had to shatter. What we have journeyed through is the story of that shattering, a cascade of spontaneous choices made as the cosmos expanded and cooled. Each critical temperature triggered a phase transition, a cosmic freezing where the universe rolled down into a new valley of stability, locking in a fundamental aspect of our reality. The first great break separated gravity and drove the inflationary smoothing of space. The next, the crystallization of the Higgs field, gave particles mass and split the unified electroweak force into the distinct weak nuclear force and electromagnetism. The asymmetry between matter and antimatter, a tiny bias in the laws themselves, ensured that a surplus of substance survived the great annihilation. Even the uniform handedness of life's molecules is a distant echo of this cosmic preference, a symmetry broken in the chemistry of the primordial earth. These are not separate, unrelated events. They are chapters in a single, continuous narrative of creative fragmentation. The flawlessness of the initial crystal was not the end of the story, it was the necessary beginning. Its breaking is what allowed for everything that followed. Without these breaks, there would be no distinct forces to sculpt the cosmos, no particles with mass to clump together under gravity, no persistent matter to form stars and planets, no chiral molecules to fold into the complex structures of biology. The universe would have remained a hot, featureless, and eternal sea of undifferentiated energy, beautiful in its simplicity, but forever silent and unobserved. The dynamic, evolving, and richly structured cosmos we inhabit is therefore a direct product of imperfection. Its beauty is not that of a static, geometric pattern, but of a symphony where a single, perfect chord has resolved into a breathtaking melody of variation. The galaxies spiraling in the void, the elements forged in stellar furnaces, the delicate machinery of a living cell, all of these are expressions of symmetry broken in specific, fruitful ways. This synthesis reveals a profound truth about the nature of reality itself. Symmetry breaking is not a destructive or tragic process. It is the fundamental creative mechanism of the cosmos. It is the means by which potential becomes actuality, how the infinite possibilities of a quantum beginning are narrowed down into the concrete, tangible world we experience. The universe did not fall from a state of grace, it differentiated itself into a state of wonder. Our very ability to contemplate this story, to trace the threads back through time, is itself a product of that same creative breaking. We are the universe grown complex enough to look back and understand the beautiful, necessary flaws in its own design. The universe's story is not one of decay from perfection, but of creation through choice. We have followed the path from a state of flawless, fiery unity to the intricate, beautifully fragmented reality we inhabit. The symmetry that holds everything together was never meant to be a permanent cage. It was a starting point, a set of perfect rules that, through their own necessity, had to bend and break to make space for something more. Those cosmic cracks gave us distinct forces, particles with mass, and a world where matter could survive. They are the reason atoms bond, stars ignite, and planets form in the quiet orbits around them. Every structure, from the vast web of galaxies to the double helix within a cell, is a signature of a specific broken symmetry, a choice the universe made as it cooled. When you look up at the night sky, you are not just seeing points of light. You are witnessing the legacy of those ancient, decisive moments. The starlight itself is a product of nuclear forces that became distinct, and the very atoms in your eyes were forged in stellar furnaces powered by the asymmetry between matter and antimatter. This is the profound takeaway. The universe's magnificence lies not in its initial perfection, but in its magnificent creative breaking. The elegant principles provided the framework, but it was their flexible, spontaneous failure that painted the rich and complex portrait of existence we are part of today. This journey reminds us that the deepest truths of reality are often found not in rigid uniformity, but in the dynamic, evolving patterns that emerge when things choose to be different. We hope this exploration has offered a new perspective on the cosmos and our place within it. If these ideas about the fabric of reality resonate with you, consider subscribing for more journeys into the heart of scientific mystery. We would love to hear your thoughts on symmetry and its breaks in the comments below. Thank you for joining this exploration of the universe's deepest